Hello dear student, in the previous session we discussed about what is increasing function and what is a decreasing function. Now let us see what is a maxima and a minima of a given function. Let f be any given function, it is defined on an interval I, then f is said to have a maximum value at a point c belongs to I if f of c is greater than or equal to f of x. Here c is any point in the interval I, then f of c, the function value at c, is always greater than or equal to f of x. F of x for all x belongs to that interval, then the point x is equal to c is called the maximum point, and the value f of c is called the maximum value of f in I. Second one, f is said to have a minimum value. Minimum means smaller value at a point c belongs to I. If f of c is less than or equal to f of x, for all x belongs to I, the point x is equal to c is called the minimum point, and the value f of c is called as the minimum value of f in I. And f is said to have a extreme value in I if there exists a point c in I such that f of c is either a maximum value or a minimum value of I in f in I, that is of f function f in I. That means it is both maximum and a minimum present for a given function, then we say that has an extreme value. The point x equal to c is the extreme point. The value of f of c is the extreme value of f in I. Let us see some problem. Consider the following function: f of x is equal to x square in the interval minus 2, 1, and g of x is equal to 1 by x on the interval I is equal to 0, 1, and h of x is equal to tan x on the interval I is equal to minus pi by 2 to pi by 2. See here, for a graph of a first function, f of x is equal to x square minus 2 square is 4. So when x is equals to minus 2, value of y is equal to 4, and value of x is equals to 1, f of x is equals to 1. So it graph like this. So f of x is equals to x square has a maximum value 4. It has a maximum value 4. It attains a maximum value at 4 when x is equal to minus 2, and minimum value is 1 when x is equals to 1. Therefore f of x is equals to x square has a both extreme value on interval I is equals to minus 2, 1. Its maximum value is 4 at x is equals to minus 2, and the minimum value is 0. Minimum value is 0 at x is equals to 0. Here 1 is the middle value, 0 is the minimum value at x is equals to 0. Next is g of x. G of x is equals to 1 by x. When is x tending to 0? When x tending to 0, 1 by x tending to infinity. Correct? When x tending to 0, 1 by x tending to infinity. So its minimum value when x is equal to 1, 1 by 1 is 1. So minimum value is 1 at x is equals to 1. But when x tending to 0 plus f of x is equals to infinity, so g of x has only minimum value, but maximum value does not exist in the interval I is equals to open interval 0, closed at 1. Next is h of x is equals to tan x. We know the graph of a tan x. This is from minus pi by 2 to pi by 2. When it comes near to minus pi by 2, it tends to minus infinity, and it comes to near to plus pi by 2, it goes to plus infinity. So there is no maximum value and a minimum value exist in this interval minus pi by 2 to pi by 2. Therefore the function h of x has no extreme value. Next is find the maximum and minimum values of the following. First one, f of x is equals to mod x plus 2 minus 1. We know that this function f of x is greater than or equal to minus 1 when x is equal to minus 2. Correct? Minimum value is equal to minus 1. When x is equals to minus 2 plus 2 becomes 0. So f of x minimum value is minus 1 when x is equal to minus 2, and f of x tends to infinity as x tends to plus or minus infinity, because x belongs to R. Whenever x increases, the value of f of x also increases. So x tending to infinity, f of x also tending to infinity. Therefore there is no maximum value for f of x. Not only for this function, every polynomial function has a no maximum value in the real number set. Real number as a domain, there is no maximum value for any polynomial. Next, second one is a sin 4x plus 3, which is greater than 0. Hence, f of x is equal to sin x plus 3. Maximum value of f of x is equals to 1 plus 3, that is equal to 4, because sin x value range value changes from -1 to 1, correct? Then 1 is the maximum value. Sine graph is like this. Maximum value is 1 and minimum value is -1. So maximum value 1. So maximum value of sin 4x is 1 plus 3, that is equal to 4. So maximum value of f of x is 4 and minimum value is -1 plus 3, that is equal to 2. Therefore minimum value of a given function is 2. Next is about local maxima and local minima, and it is also called as a relative maximum and a relative minimum. A function y is equal to f of x is said to have a local maxima at c. Then f of c is greater than or equal to f of x for all x in some open interval containing c. And a function y is equal to f of x is said to have a relative minima at point c if f of c is less than or equal to f of x for all x in some open interval containing c. If the function has either a relative maximum or a relative minimum at c, then f is said to have a relative extremum value at c. For example, the function f of x is equal to sin square x attains the local maximum value 1 infinitely many times, because the sin square of 2n pi plus or minus pi by 2 is always 1 for any integer n, and 0 less than or equal to sin square x less than or equal to 1 for all x belongs to R. Similarly, it has a local minimum value 0 infinitely many times, because sin square n pi is equals to 0. Now let us discuss how to find the extreme value of a given function if exist. Here three graphs are given. See here, if f of x is a relative extremum at c and f dash of c exists, then the graph of the function must have a horizontal tangent line at the point x is equal to c, and hence f dash of c is equal to 0. In figure 1 and 2 we can see that there is a horizontal tangent present in this and this. Therefore f dash of c exists. If f dash of c exists, then horizontal tangent also present. Suppose f of x has a relative maximum at x is equals to c, then when x is less than c, f of x is increasing, and when x is greater than c, f of x is decreasing. Therefore when x is less than c, f dash of x is greater than 0, and when x is greater than c, f dash of x is less than 0, that is f dash of x changes the sign from positive to negative. Similarly, it can be seen f of x has a relative minimum at x is equals to c if f dash of x changes the sign from negative to positive. These are the main two conditions, that is f of x has a minimum, then the sign changes from negative to positive, and if it is a maximum, the sign changes from positive to negative. In a figure 3, f of x has a minimum at c, but f dash of c does not exist. However, f dash of x changes the sign from negative to positive. Thus, we observe that if a function f has a local maximum or a local minimum at x equal to c, then either f dash of c is equal to 0 or f is not differentiable at c. Such points are called a critical point. So, critical point definition is a interior point c of a domain of a function f where f dash of c is equal to 0 or f dash of c does not exist is called as a critical point. So let's see some important statement. Let f is a function defined on an open interval I. Let f of x is a continuous at a critical point x equal to c, then f dash of x changes the algebraic sign from positive to negative, then x has an increasing function through c, then f of x is a has a relative maximum value. If f dash of x changes algebraic sign from negative to positive as x increases through c, then f of x has a relative minimum. If f dash of x does not change the sign, x increases through c, then c is neither a point of a local maxima nor a point of local minima. Let us see some problem. First one, find the local maxima and local minima of f of x, where f of x equal to x cube minus 6x square plus 9x plus 1. So f dash of x is equal to differentiate with respect to x. Differentiation of x cube is 3x square minus 12x plus 9. So f dash of x is equal to 0. So 3x square minus 12x 12x plus 9 is equal to 0. After factorizing this one, we get x minus 1 into x minus 3 equal to 0. That implies x equal to 1 comma 3. These are the critical point. For these 2 points, when x is less than 1, f dash of x is equal to, when x is less than 1, f dash of x less than 1 means less than minus 1 is, this is negative, this is also negative. Negative into negative is a positive. When x is a greater than 1, f dash of x is equals to positive into negative is equal to negative. It changes the sign from positive to negative. Changes the sign from positive to negative means it has a local maxima. So f of x has a local maxima at 1. So f of 1 is equal to 5 is 5 is the local maxima. When x is less than 3, f dash of x is equals to positive into negative, that is equal to negative. And when x is greater than 3, f dash of x is equals to positive into positive, that is equal to positive. It changes the sign from negative to positive. Therefore it has a local minima at x equal to 3. So f dash of x has a local minima at f of 3. F of 3 is equal to 1. Second one, discuss the maxima and minima of the function y is equals to x minus 4 whole to the power 5 into x plus 2 whole to the power 4. We have to find dy by dx. Dy by dx is equals to, here we have to use the product rule. 5 into x minus 4 whole to the power 4 into x plus 2 whole to the power 4 plus x minus 4 whole to the power 5 into differentiation of x plus 2 whole to the power 4 is 4 into x plus 2 whole to the power 3. So x minus whole to the power 4 into x plus 2 whole to the power 3 is a common, left with the 5 into x plus 2 plus 4 into x minus 4, that is equal to x minus 4 whole to the power 4 into x plus 2 whole to the power 3 into, after simplification we get a 9x minus 6. So dy by dx is equals to 0. So x minus 4 whole to the power 4 into x plus 2 whole to the power 3 into 9x minus 6 is equals to 0. Therefore x equal to 4 comma minus 2 comma 2 by 3 are the critical point. When x is less than 2, dy by dx is a positive. When x lies between minus 2 and 2 by 3, minus 2 and 2 by 3, dy by dx is a negative. Here sign changes from positive to negative. Therefore x equal to minus 2 is a maximum pointer. Therefore maxima is equal to 0. That is equal to f of minus 2. When x is lies between minus 2 by 3 comma 4, we get positive value. Here x is less than 2 by 3, it is negative. X is greater than 2 by 3, which is positive. Therefore it has a minimum at 2 by 3. Therefore minima is equal to 10 power 5 into 8 power 4 divided by 3 power 9. When x is greater than 4, its value is positive. Here less than 4 is also positive, greater than 4 is also positive. That means dy by dx does not change the sign as x passes through 4, hence y has a neither maximum nor a minimum at x equal to 4. It has a point of inflection. Next is the second derivative test. Let f be a function defined on the interval I. Let f be a twice differentiable at c belongs to I. If f dash of c is equals to 0, f double dash of c is less than 0, then f has a local maximum at x equal to c, and f dash of c is equals to 0, f double dash of c is greater than 0, then f of x has a local minimum at x equal to c. The test fails if f dash of c equal to 0 and f double dash of c is equals to 0. Find the local maxima and minima of f of x is equal to x to the power 4 minus 8x cube plus 22x square minus 24x plus 12. So f dash of x is equals to 4x cube minus 24x square plus 44x minus 24, and f double dash of x is equals to 12x square minus 48x plus 44. So f dash of x is equals to 0, then we get the x value as x cube minus 6x square plus 11x minus 6 is equals to 0, where x is equals to 1 is a root, because sum of the coefficient, that is 1 minus 6 plus 1 minus plus 11 minus 6 is equal to 0. Therefore x is equal to 1 is a 1 root. If x is equals to 1 is a 1 root, by division method we can see the another two roots, that is x minus 1 into x minus 2 into x minus 3 is equals to 0. Therefore x is equals to 1, 2, 3 are the critical value. So f double dash of 1 is equal to 12 minus 48 plus 44, this is greater than 0. Therefore f of x has a minimum. So f dash of 1 is greater than 0, therefore it has a minimum at x is equals to 1. The minimum value is f of 1 is equal to 3, and f double dash of 2 is equals double dash of 2 is less than 0, therefore f of x has a maximum at x equal to 2, therefore maximum value is f of 2, that is equal to 4. And similarly f double dash of 3 is greater than 0, therefore another local maxima is there, that is at 3. The local maximum value is f of 3 is equal to 3. Next problem, show that x to the power 5 minus 4 into x to the power 4 plus 5 into x power 3 minus 1 has a maximum at x equal to 1, minimum at x equal to 3, and neither a maximum nor a minimum at x equal to 0. So f of x is given x power 5 minus 5 into x to the power 4 plus 5 into x power 3 minus 1. See f dash of x differentiate with respect to x. 5 x power 5 is 5 into x to the power 4, 5 4 is 20 into x power 3 plus 5 3 is 15 x square. F double dash of x is equals to 5 4 is 20 x cube minus 23 is 60 x square plus 15 2 is 30 x. Equate f dash of x to 0. F dash of x is equal to 0. 5 into x to the power 4 minus 20 x cube plus 15 x square is equal to 0. Here 5 x square term is common here. 5 x square into x square minus 4x plus 3 equal to 0. That implies 5x square. On factorizing this equation, we get x minus 1 into x minus 3 equal to 0. Therefore, x equal to 0, 1, 3 are the critical point. Substitute the critical point value to f double dash of x. So, f double dash of 0 equal to 0. Therefore, f of x has a neither maximum nor minimum at x equal to 0. F double dash of 1 is less than 0. Therefore, it has a maximum at x equal to 1. And f double dash of 3 is greater than 0. Therefore, f of x has a minimum at x equal to 3.